The next paper will be delivered by Professor Hagelstein from MIT, and it's entitled Lattice-Induced Nuclear Excitation and Coherent Energy Exchange in the Karabut Experiment.
I've been working on the theory for this stuff like seemingly forever. I was a late starter, and I feel like I got started a day after the announcement. I started the same day of the announcement. The cold fusion excess heat deflection Ponce experiment presents a challenge for the theorists. Probably you can imagine that you're an experimental, so all you have to do is replicate an experiment. And theorists figuring out how it works.
Microphone?
I have a microphone. Just hold it. How about that?
That's better. Thank you.
Okay, thank you. Okay, so I've had some luck lately. I wanted to share that with you. In the case of excess heat production, the big headache is that there's no chemical products in amounts commensurate with the energy, nor energetic nuclear products commensurate with the energy. So from my way of thinking, the energy is going starting from a nuclear degree of freedom and going into a condensed matter degree of freedom. That's not an easy thing to do. And I've been looking into the models that fractionate a large quanta to break it up into small quanta. If you could do that, there would be no problem accounting for cold fusion. In 2002, I came up with a toy model, lossy spin boson model, that was able to fractionate a large quantum. That's very exciting. However, it's been difficult trying to get a physical model that reflects this. So when I was presenting earlier, years ago at conferences, I showed simulations that would show the energy going from the deuteron to helium-4, 2 deuterons to helium-4 transition and going into the oscillator, highly excited vibrational mode. And then in the simulations, it would go back the other way. And noted contributor to the field, Akito Takahashi, who's not only a superb experimentalist, but a rather good theorist as well. He points out and he says, look, it's okay for the energy to go from the nuclear transition to the oscillator, but it's never going to go the other way. That's impossible. Can't do that. And as it turns out, I'm still reflecting on Akita's input, which I'm very grateful for. So it seemed to me that if you actually wanted to make the case and prove it to somebody, that would be exactly what you want to do. You want to start with a physics experiment where you put energy into vibrations and give it to the nuclei. So I set about trying to use my models to design such an experiment. So the first step is to figure out which transition to aim for. The idea is that it's harder to transfer a large amount of energy, so we want to transfer the smallest amount of energy that we need to. And the model requires a stable ground state. So here's the lowest energy transitions from stable nuclear ground states, and Mercury 201 comes up sort of singular in this. So I said, let's focus on transferring energy to Mercury 201. So conceptually, the idea is to take a sample that has some Mercury 201 in it, put in vibrations, calculate a way, design, and you excite the Mercury 201 nuclei, and if they're excited in phase, or radiate in phase, you get a collimated beam coming out due to phased array collimation effect. It's not a laser, it's just a lot of antennas radiating in phase can make a directional beam. So I worked on this and did the design. So the model suggested that this was a reasonable idea. You could execute the design. Collimated emission would be expected. The line would be very broad. But the early models said your sample had to be meters, driven by terahertz, and a very exciting experiment. At some point, it occurred to me that a friend of mine, Alexander Karabut, showed up at a conference in Cambridge and said that he had collimated emission at 1.5 keV in his glow discharge cold fusion experiment. And he said he'd made an X-ray laser. Some of you who know what I did before cold fusion probably know that, well, I worked on X-ray lasers. And I looked at that and I said, there's no way in the world that that could be an X-ray laser. There's got to be something else. So imaging down on the cathode, you get this. This is the size of the cathode. The X-rays seem to be sourced from the cathode. There's actually, in my view, two different effects in Karabut's experiment. During the discharge, there's diffuse emission that goes to the side, which I think is stimulated by collisions with incoming ions and involves optical photon mode excitation. So here's the spectra, and he made a discretized version of it, and it sort of peaked around 1.5 kilovolts. And the line width is very broad, which, by the way, corresponds to what the model predicts. In fact, in this case, the model says if you drive it really hard, the line gets broader. If you drive it less hard, the line gets narrower. So here's some data. The line's being driven not very hard, and the line's fairly narrow. The line's being driven much harder, and it's broader. And when I saw that, I thought, well, if it walks like a duck, if it, oh, you know the story. The collimated emission looks something like this. You get a narrow collimated beam to different energies over a broad line width, and that has to do, in my view, with the superradiant emission dynamics. So the idea is, number one, could understand Fleischmann ponds if we could fractionate a large quantum. We could, I'm interpreting the Karabut experiment as being an example of showing conversion of vibrational energy into nuclear energy, upconversion. Can we model it? Well, the early models were short by orders of magnitude. It's very hard to get coupling to be strong enough. So I said, let's use the Karabut experiment to debug the model. So effects predicted by the toy mathematical model. Can we get it from a first principles model? That's the goal. About 1.5 years ago, we came up with a new fundamental model, which I thought would do the job. In the spring of last year, analyzed it, but failed to get agreement. I was off by a factor of a few hundred, which in this field is pretty close. In the summer, I found a model which was spot on with experiment. I was all excited, and ICCF president, I got up and I said, here it is, we got agreement between theory and experiment. And then when I wrote it up, I found it to be an error. Very technical. I'll explain it like another day. 8 months or more worth of very hard work exploring very tough models has led now to a resolution. And I want to explain the resolution. I think we now have a model that might actually do the job now. And that's what I'm excited about. The basis of the model rests on the notion of a relativistic composite. The idea is that, well, QCD, you get complicated wave functions. If you make a basis state expansion and take all the energies in the rest frame, put it in a big matrix here, positive energy states, negative energy states, like everything, mathematically complete. If it accelerates, then you mix the rest frame states with, well, you mix one state with another state. And that's what this matrix does. And if you like, that's my theory. That's the model. This, I'm proposing that this does the job. You need essentially nothing else. So now if you model nuclei, use this model. It's sort of a little bit like a Dirac model, but it's bigger. And just plug that in for the nuclei, electrons, nuclear, electron, electron, nuclear, electron. There you go. It seems to me, and I'm of the opinion now, that this does it. You need very little more. And this gives you the anomaly systematically. Now, I haven't proven it throughout for all cases, but I do have an example now for one case, which I'd like to share with you. One at issue is to calculate these coupling matrix elements, which, well, they would follow directly from a QCD calculation. So all we have to do is wait for the QCD folks to model Palladian, anything else. However, there's a shortcut. I have calculated two of these matrix elements so far. I've calculated transitions of the deuteron and the DD going to helium-4 transition. I'm now convinced both of those matrix elements are too small by a factor of more than 50. To get a better answer, if I replace the nuclear Hamiltonian using the same trick, model protons and neutrons as relativistic composites, use empirical potential, that should be sufficient to calculate systematically the nuclear coefficients for the model. Now that's the theory. There's a documentation paper that's been accepted, will appear in print, so this is a very short abstract of it. But from the fundamental Hamiltonian, it's a quick derivation to a lossy spin boson model, which we've analyzed in depth. We can analyze it by doing basis expansion. What was new is that this time I analyzed all the constraints before I got 2 out of the 3. And 2 out of 3 doesn't do the job. You need the third one to get agreement with experiment. And I hadn't done that before. So we can solve the constraints, get self-consistent solutions. What's new is we get 2 distinct regimes of operation. One's conventional, and in the conventional regime, hardly anything happens. One's an anomalous regime, and in the anomalous regime, the coupling between the nuclei and the oscillator, well, it generates virtual phonons. And when you have more virtual phonons than you have real phonons, then the system does the work for you. You don't have to pound on it very hard. It's astonishing. So fractionation's much easier in the anomalous regime. So from the models, we get a simple formula for the rate. It's basically a nonlinear Rabi oscillator, and this is the Rabi part of it. Then there's a hindrance factor. And the hindrance factor works like this. When your coupling's strong, the hindrance factor is 1. If your coupling's weak, nothing happens. So this part of the problem determines whether you can fractionate the quantum exchange, the energy. So if you like, that's the hardest thing to do. If you can do that, everything else is straightforward. So the question is, can we do it? What's the constraints? So after a lot of analysis, for a simple monatomic lattice, the constraint looks like this. So in the conventional regime, we get this. In the anomalous regime, we get this. This depends on the number of phonons. Here, this is the number of virtual phonons. And otherwise, there's factors. There's only 4 parameters in this model. Number of oscillator quanta, number of, the amount of fractionation. Delta n's the number of quanta that you get after fractionating. 1, 2, there's this R parameter, which tells you something about how strongly coupled it is and tells you whether you're in the anomalous regime or not. And it only depends on the coupling strength, the masses, and how many of them there are. So if I try to model Karabut experiment in the conventional regime, I get this plot. And basically the way to understand this plot is that if your lattice is highly excited and you have a lot of atoms around, you can transfer this much energy. To get the mercury excited, we need 1.5 kilovolts. Here we've succeeded in getting 1 volt. This is starting from 100 megahertz, which is like 10 to the minus 7 volts. So we've actually done a lot, but we're far short of explaining Karabut. This is what I got in spring of last year and was very depressed. It's before I found the anomalous regime. And the anomalous regime works like this. Once you have more virtual phonons than real, you get to be insensitive to how highly excited it is. Up here, this, as assumed that I've taken mercury sample, alt mercury 201, spin aligned it, put in a liquid nitrogen bath and vibrating it. How many atoms are needed to fractionate 1.5 keV quantum? It's this number, about 5 times 10 to the 17th mercury 201 nuclei. So this looks good. However, now I want to come back to the Karabut experiment. The Karabut experiment, in one case, in the case of niobium, there's a transition which looks to me like it can fractionate the quantum for me. And Karabut worked with the niobium sample, and he didn't tell me how thick it was, but if I assume 25 microns, which is typical for those kinds of samples, the resonance of the compressional mode of the fundamental is around 100 megahertz. And this is the fractionation power, or the energy that you can fractionate, given how many niobium atoms you have. So in Karabut's sample, you have about this many, which gives you a fractionation energy of about 5 keV. And Karabut's data has fractionation, has collimated emission on lines up to 4 keV. So, in my view, you have to be in the anomalous regime to be relevant to Karabut. Niobium, there's a transition which probably can do the job. Agreement for the very first time after 300 previous dead models buried in the backyard. I have a model which is getting an agreement. Thinner samples, higher frequency, higher sound speed can go to higher energy. But there's other agreements as well. Karabut saw this effect for many different metals, not just niobium. And that's very hard to understand from conventional nuclear models. But on the other hand, if we work with nuclear models based on a relativistic composite Hamiltonian, it's not hard to understand at all, which means we're going to need the new nuclear models to calculate the A matrix coefficients. The scaling is very favorable in the terahertz regime, and the numbers from this model is actually reasonably close to what was presented last year at ICCF-18, where we basically found pretty good agreement for excess heat from these models, also for GOT-C emission near 90 kilovolts, and Piantelli's conversion of the M4 transition in barium-137 at 661 keV. Scaling is very favorable to the terahertz regime, and I think these models, without much heroics, allow us to model correctly excess heat, Fleisch-and-Pons experiment, gamma radiation, Karabut. I was upstairs looking at the posters, and poster after poster, the posters are very interesting. And I was walking along, and I saw a poster, and the poster had collimated X-ray emission, 1.5 kilovolts. Walking along, I just stopped. What? And it turns out I got very excited, and I twisted my friend Vladimir Vysotskii's arm to tell me all about his experiment for an hour and a half. And I was presenting his poster to my friends because I was so excited. And I came and I twisted Rob Duncan's arm, and Rob Duncan very graciously agreed to donate Graham Hubler's 20 minutes to Vladimir. Oh wait, no.
Back for questions.
I competed for the possibility to make the alternative or a different point of view on the nature and reason of X-ray radiation that was observed in many experiments during the last 10 years, for example. First of all, during such period, were published many works in which approximately or very close results were presented. The main idea is following. Was observed soft X radiation with maximum in the area from 1 up to 2 keV. In many cases, this X-ray radiation was registered outside of working chamber and on other side of very thick screen. For example, typical experiment was a Karabut that was discussed below. Our point of view is the following. In our opinion, such process not related to the laser-oriented phenomena and not related to excitation of any isotopes. Our results were published in this article and very briefly describe of our experiments. During the last 5 or 6 years, we have conducted experiments on analysis of radiation process during the process of formation of excitation bubble. First several experiments were conducted on such system. It is a circulation machine oil. It is a working chamber under some pressure. Machine oil moving through this channel. And in this working chamber, we have observed very strange phenomena. It is a view of working chamber. This for different pressure, more low pressure, more high, and pressure more, for example, 80 atmosphere. In this case, you can see that, next figure more, you can see that we have observed the formation of very intensive white-blue color lighting stream. What is the nature of such stream? Because it is usual machine oil. First idea was the following, that is, maybe it is connected with the Cherenkov radiation of fast electron, because in this system, the high voltage generation high voltage place because the dielectric channel and machine oil. But action of transversal magnetic field leads to such field not influence on the property of this lighting. Also was idea that maybe such phenomena connected with sonoluminescence, but well known that sonoluminescence has very low intensity. Was idea that maybe it connected with formation of a laser system, because during such high pressure the process of formation inverted state of molecular take place, but is also not related to laser. Our new idea was investigated the property outside of chamber, because the very thick wall of chamber, it is made of plexiglass with thickness about 7 centimeters. It is a position of X-ray dosimeter, such gamma detectors, and it is a method of calibration these dosimeters. And in first experiment we have observed immediately that near surface of chamber, on the large distance from area of cavitation, we have observed very intensive X radiation. X radiation from plexiglass with energy about the same area, 0.5 keV. Also, we have some different modification experiment, and we have added some copper powder on the surface of chamber. And in this case, it was a peaks of radiation without such powder copper, and with presence of copper, we have registered very intensive peak with the energy about 4 keV. If we have used the very thin foil made from copper, we have the suppression of weak part, and we have very intensive X-ray radiation generation with the same energy. Next step. In our opinion, in this process, in this system, has the following process. During motion of machine oil through such channel, the process of formation of cavitation bubble take place in moving stream. After process of cavitation and explosion of cavitation bubble, the process of formation of shocking wave take place. Such shocking wave acts on plexiglass wall and generated additional secondary shocking wave. Motion of shocking wave and reflection from external surface lead to excitation of atom on the surface, and spontaneous radiation that connected with such excited atoms lead to generation of X-ray radiation. We have investigated by different methods the nature of such radiation. For example, we have used distance dependence dependence of intensity radiation versus distance from surface of such chamber, and also from this analysis follows that it is real radiation with energy about 3.5 keV. Next one, what is the nature of such transition? It's connected with shocking wave. On this figure you can see the analysis of from piezoelectric from the surface of plexiglass chamber. Next steps. It is very interesting, the process of generation of bubble. Usually it is stochastic process, but in this case we have in fact generation on a van der Pol generation coherent packets, coherent burst of cavitation bubble. It connected with very interesting phenomena during process of cavitation. Excited elastic wave not lead to the generation of X-ray radiation on the channel. It is effect positive Big Bang. We have the loop of positive Big Bang and formation classical from the radioelectronics generator van der Pol. It leads to modulation of beam and modulation of process of cavitation phenomena. Next experiments were conducted with analysis of X radiation from the stream of usual water, not machine oil, because it's more simple. We have used well-known system, special industrial system for coating metal and stone is the system. And we have used the water stream from such system. In such system, the pressure was from 2.5 atmosphere up to 2000 atmosphere, but usually we have used pressure about 200 up to 300 atmospheres. At the approximately position of a detector near the water stream, it is water stream and detector, and in the first regime, in the first experiment, we have observed very interesting phenomena, absolutely abnormal phenomena. On the left figure, you can see X-ray radiation from the surface of water. It is X-ray radiation from water with energy about 1 keV. On this figure, you can see the X-ray radiation from surfaces of metal tube. Approximately, first radiation was from this position, second from this position. So we have a shift of the energy of X-ray radiation dependence from the role of material. Next step was the following. We have to add some very thin layer of plumbo powder on the surface of metal tube. If we have registered the X-ray shift of X radiation light up to energy 5 keV. So the spectrum of such radiation don't depend on the regime of water, on the pressure of water. It doesn't influence or acts only the intensity of X radiation, but not position. Position is dependent only on the kind of atom. We have conducted many different methods of registration. For example, is the result of an analysis of X radiation in such system using two photoplate that was put in one black envelope in the form of cylinder and situated approximately in this position. After exposition, we have registration of X-ray radiation on both photoplates. First, of course, was more black, other many black, because the process of cell absorption takes place. Yeah. Also, it is very interesting, absolutely abnormal experiment. We have used in this position the tube, with metal tube with cavitation water, and also there was from one side on the distance about 3 centimeters was put there as thick metal steel with thickness about 3 millimeters, and 2 photoplates in the same envelope. On other side, we have put 2 photoplates in one position, symmetrical, and other one. And after exposition, the result was paradoxical. On the photoplate that was situated in free space was no signal. All 4 plates were totally white. But the photoplate that was situated over the very thick steel plate, silk screen, we have observed very intensive signal, but this is a very interesting form made of a small pin, but without very small angular divergence. It is very interesting nature of such phenomena because it is view photos of a steel screen. It is one side was without paint and another side was paint without some defects. And the lower part of the screen was made from paint because was used for fixation of such system. So let's consider this black signal is related to the area where paint was absent, and all this black signal is connected with the defects in the paint on the surface. There is some description, have no time. Very interesting that we have put our screen with rotation on 180 degree. For example, rotation, one position, it is a paint, in other. In one case, we have observed very interesting signal, very intensive signal. Other case, no signal. What is the absolute abnormal result? This is connected with a very interesting process of step-by-step transformation, shocking elastic wave to X-ray wave, and from X-ray wave to elastic wave. Here is the 3 steps. It is a cross-section of the source of our X-ray. X-ray was very weak, soft. It's less about 1 keV. Very strong absorption on a short distance. Absorption of intensive X-ray lead to formation of shocking wave. Shocking wave moving to the internal surface of screen. Process of interaction, secondary shocking wave take place. And reflection shocking wave from the back side of the screen lead to generation excitation atom and degeneration of X radiation. Because the front of shocking wave is close to the plane, the process of excitation is coherent and lead to the formation of phase-dependent distribution of excited atom and generation of quasi-plane Röntgen X-ray wave with very large transversal coherency. So there are different results. We have, by this ideology, we have created the system of metal lens for focusing and defocusing X-ray radiation. In usual Röntgen optic is traditional point of view, it is absolutely point. It's possible. But because the part of optical wave is in traveling in the form of elastic wave, as is a Röntgen wave, it is possible using such phenomenon. For example, it is a focusing X-ray and defocusing X-ray. Yeah, very close. So it is following from our analysis that the spectrum of X radiation that we have observed in our experiment absolutely similar to the spectrum of Karabut. In our opinion, the reason of X radiation in Karabut light experiment not connected with low Lambda phenomena, but connected with the process of formation of shocking wave during explosion of cracks at glow discharge or loading of metals. So it is, we have conducted also experiment on the analysis of shocking wave on the surface of such chamber. No, it is very simple, and quantum mechanical analysis has shown that such process is possible, and reflection of shocking wave, the process of excitation atom is, it's real fact of quantum mechanics, very simple. Thank you for the attention.
Really intriguing. I'm sorry that we're so tight on time, but is there like one or two quick clarification questions? I mean, this is going to take me a lot of time to dig into yours to understand. But very
So
intriguing.
Peter, if you reverse the process and that, are you going to tell us what X-ray frequency you need for ablating the stimulated?
I presented on this before. The 24 MeV quantum gets subdivided, so you've got different transitions of much lower energy. So, for example, when niobium was good, I think a year ago I was keen on.
So I was talking about whether you excite the materials with X-rays.
No, I don't think there's. I mean, if you have a
Did the opposite.
no, if you have a synchrotron and you excited mercury 201
Yeah.
and got a good excitation, then it should be possible to convert that to vibrational energy to go the other way. This should go back and forth both ways.
I'm sorry, we have a lot of questions. What I'd encourage, this has been very intriguing, and I hope it results in a lot of offline discussion, because I certainly know I've got a lot of interest too. But the reason why I say this is that we have to rush on, because if we don't, it will be too late for, again, arranged tours.
I want to thank Graham for donating this time to Vladimir.
No, thank you, Peter. Very, very